No radio, no IDs for Russian hulls tightening to 8 nautical miles. Textbook encirclement. You're in the right video. This is the USS Porter's standoff in international waters. Here's what we'll deliver. How the Russian-Soviet-era doctrine fractured their coordination. How Porter's Aegis fused every signal into a single brain, and why launching one MH-60R halted the squeeze. Keep watching to learn why numerical ship counts mean less than networked vision, and how the US walked away with data on 4 classes while conceding nothing. 4 contacts at 26 nautical miles. No radio, 4 bearings closing. So why did Porter keep her course and speed when every instinct says, turn away? Because the first move in a 4-on-1 pincer isn't helm over, it's math. International waters north of the Greenland sea lanes look empty until your scope fills with steady blips and your watch officer calls out new plots. Porter's routine patrol started as a clean transit along merchant routes used by tankers exiting the Barents Gap and container ships edging the ice margin. Then the tracks began to firm up. Bearings stabilized, ranges ticked down in predictable steps, and the board told a story, converging vectors without a single hail. The tone on the bridge shifted from casual reporting to measured cadence, positions, speeds, headings, handed to CIC while navigation kept the ship steady. No one rushed. No one raised the volume. What closed the gap weren't random patrol boats. The signatures and silhouettes resolved into a known mix: 2 Udaloy-class destroyers and 2 Admiral Grigorovich-class frigates. They didn't declare intentions or request deconfliction. They built a box. One pair nudged in from the starboard quarter and forward starboard bearing. The other mirrored it from port, each leg sliding along the edges of a loose rectangle that tightened with every minute. No whistles, no bridge to bridge, just hulls, wakes, and deliberate geometry. On the plotting boards and screens, the problem reduced to lines and times, bearings at 040 and 130 to starboard, 230 and 320 to port. Closest point of approach estimates started in the teens, then trended toward single digits, 11 nautical miles, 10, then 9.2. A pincer doesn't need to cross your bow to create stress. It needs multiple vectors that force you to divide attention, complicate turn options, and tempt an early maneuver that seeds initiative. One wrong turn shortens a leg and hands the opposing side a closer CPA on the next pass. A calm helmsman and tight comms beat a reactive rudder. The rules of the road don't disappear in tense water. In international seas, collision avoidance rules govern stand-on and give-way behavior based on crossing, overtaking, or head-on situations. None of the Russian tracks crossed into a collision course. No constant bearing, decreasing range toward a 0 CPA. So mandatory maneuvers never triggered. That's the pressure point. They can push to near without entering must. They skate the edge of a rule set that punishes careless moves but doesn't forbid a box built at 8 nautical miles. That's well inside the gray zone playbook. You keep it legal, you make it crowded, and you dare the other side to blink first. Intimidation through proximity, not through violations. One helmsman's hesitation, one nervous course change, and you seize a narrative of control. But the flip side of silence is that it speaks. Every hold of a radar mode, every engine setting inferred from wake length, every gradual heading change says something about training and intent. Porter didn't need chatter. She needed consistency to pull threads from the pattern. As the CPA slid toward 8 nautical miles, the bridge and CIC locked into cadence. The navigator kept a steady base speed. The conning officer held a course that preserved sea room to both flanks. CIC filtered sensor returns, scrubbed for false echoes, and validated plots with ESM bearings. That synchronized rhythm looked like a lack of reaction from the outside, but it set the pace inside. The watch teams updated tracks on the minute, reran CPA math, and shared only the necessary calls over the net. No rushed orders, no hard-over dramatics that could be read as alarm. The mini payoff arrives quietly. Porter's composure dictates the tempo. The Russian formation decides how close to slide. It doesn't decide how fast the situation evolves. The sensors set the clock. With each sweep and each bearings only update, the box stops being a trap and becomes a data problem. And a data problem is solvable without touching the helm. That leads to the real question. If one ship can hold steady against 4 hulls by turning a squeeze into a stream of tracks and timings, what kind of brain lets a single combat system make that many opponents feel late to their own maneuver? How does one combat system make 4 ships feel blind in open water? By turning the ocean into a spreadsheet, the instant a radar pulse leaves the array, and by delivering answers before the other side finishes asking the question. Aegis on Porter acts like an integrated brain. The SPY-1D radar feeds raw returns. The electronic support measures suite listens for emissions. The navigation and identification systems layer context. Weapons control doesn't wait on a separate chain. It sits in the same loop as the sensor picture. Command decisions ride on a fused display, where tracks, priorities, and engagement options update without human relays. That fusion keeps the bridge and CIC in the same second, not the same minute. Across the water, doctrine splits the load. Each Russian hull runs its own sensors, its own fire control logic, and its own operator interpretations. Data sharing exists, but it is limited by link compatibility, bandwidth, and the habit of local control. Voice nets carry intent, not raw sensor data. So 4 ships equal 4 partial views that need reconciling before a unified action occurs. Every reconciliation step is a delay. Every delay widens the gap between what is happening and what they think is happening. SPY-1D changes tempo with coverage and track quality. Its phased array sweeps build hundreds of tracks at once and refresh them in tight cycles. The system can manage well over 1,000 objects, but count is not the trick. Quality is. Aegis pushes each contact toward a higher fidelity state: firm course, reliable speed, stable altitude if airborne, and a confidence score. That quality lets one ship decide whether a dot is clutter, a decoy, or a shooter, without stopping the plot to argue. Sensor fusion does the heavy lifting. Radar plots provide range and bearing. ESM vectors add who is transmitting and how. Link networks bring in offboard cues from other nodes. Correlation rules bind them, promoting consistent tracks and demoting noise. Decoys that try to spoof range with clever waveforms fall out when ESM notes the mismatch in pulse repetition or beam shape. A contact pretending to be 2 targets merges when range rates line up across sensors. The fog thins, decision speed follows naturally. CIC operators on Porter do not pass notes down a line. They act inside one interface. Classification tables, threat libraries, and weapon doctrine are all at hand. A query becomes a mark on a track file, not a request that waits on a reply over a busy voice circuit. 4 independent captains can coordinate, but coordination takes seconds they cannot spare when closure rates compress timelines. By the time they settle who owns which contact, Aegis has already adjusted priorities and set guard windows on the next move. Even silence is a message. Aegis logs electronic emissions automatically. Range gates, pulse repetition intervals, scan rates, and beam patterns stack into a library with timestamps and bearings. Change a mode, and the log catches the delta. Shift a search sector, and the system notes the new dwell. Those signatures become fingerprints that help sort classes, specific platforms, and operator habits. Each pass adds depth to the library and shrinks the mystery the next time. As the Russian group tightens, their nodes try to assemble one picture. But independent sensors working through limited links create timing seams. One ship updates on its own sweep rate, another on a slower cycle, a third waits for voice confirmation. Those seams show up as jitter in track positions and as hesitation in maneuvers. Porter's picture stays smooth because every sensor feeds the same clock and the same correlation logic. Smooth beats loud. That is the payoff. Intimidation becomes telemetry. The 4 hulls provide angles, emissions, and timing tells. Aegis collects, classifies, and preserves. Threats stop being a mystery and turn into well-labeled files ready for action or analysis. So if the brain owns the picture and sets the pace, the next question is simple. Which side's muscles actually matter when range, integration, and targeting math start to bite? 4 ships look like a wall until you sort the numbers that decide who can hit, who can see, and who can guide a weapon onto a moving target. Range gives you a first move. Integration turns that move into a chain. Targeting math makes the shot real. If any one of those breaks, mass turns into noise. Start with the Udaloy destroyers. They were built around anti-submarine warfare. Their big strengths sit below the surface. Long-range sonar, helicopter support for dipping sensors, and the SSN-14 system, meant to chase subs, and, in some variants, threaten surface contacts in a pinch. On the surface, they carry 100mm guns and older short-to-medium air defenses sized for self-protection, not wide-area cover. They can throw a lot of metal, but the reach and update rate of their targeting tools is tuned to track diesel boats and nuclear subs, not to run a coordinated surface engagement against a networked opponent. Their radars can detect and track a destroyer-sized contact, but turning that track into a reliable fire control solution at distance demands stable updates and external cues they rarely get in real time. Now layer in the Admiral Grigorovich frigates. These carry Kaliber missiles with serious land attack range and respectable anti-ship variants. The catch is the targeting chain, to use that maritime strike potential beyond the radar horizon. With confidence, they need external targeting or highly accurate over-the-horizon updates. Without a higher node feeding exact positions and course changes, a long-range shot becomes a guess that risks outrunning the data. In a cluttered surface picture, even a good seeker wants a clean handoff. If that handoff degrades, crews face a choice: hold fire and shadow, or shoot and risk a miss that gives away tactics. Here's the hinge in the scenario. Each Russian hull largely runs on its own sensor picture. They can coordinate by voice and share some linked data, but those pipes are thin, and doctrine keeps control local. When four ships don't share raw tracks and correlation logic, they fight four parallel fights. A higher node, a shore station, a patrol aircraft, or a satellite uplink can stitch it. Yet latency, coverage gaps, and emission control rules often keep that stitch loose. Every second of delay turns fast-moving bearings into stale cues. Porter doesn't just see farther, she sees together. A networked combat system pulls radar, ESM, and links into one file, assigns track quality, and preserves custody through maneuvers and clutter. That means she can push targeting quality data to her own weapons while denying clean solutions to ships that can't merge their sensors at the same speed. Denial doesn't mean jamming every signal. It means offering no steady, continuous track at the range they need. Small, deliberate course and speed changes reset their fire control timelines. Tight emission control keeps them guessing which sensor mode to trust. The result is simple. One side lines up a shot, the other keeps reacquiring. There's a simple meter for pressure that rarely gets mentioned: fuel burn. A four-ship Russian group can run roughly $5,000 an hour in operating costs just to keep the hulls moving, sensors on, and crews at stations. Intimidation isn't free. The clock runs whether they gain position or not. Extend that to 40 minutes, and you've spent tens of thousands to turn circles and gather no firing solution you trust. The wake marks fade, the accounting does not. Doctrine drives expectations. Russian crews look for psychological leverage, crowd the chessboard, force a move, claim control of the scene. Porter's calculus values custody of tracks, signal characterization, and measured tempo. She doesn't buy a headline. She buys data that makes the next hour, and the next encounter, easier to manage. When range and integration sit on one side, and mass without shared targeting sits on the other, numbers lose their edge. Four hulls without a unified picture become four sources of telemetry for the ship that fuses faster. That's the quiet payoff. Range plus integration beats numerical presence because only one of those changes the quality of a firing solution. Blunt mass pushes water. A network shapes time. And the moment that balance became obvious on those cold lanes wasn't tied to a missile ripple or a hard turn. It hinged on a single launch that shifted reach from decks to air. Why did one helicopter change four captains' minds at once? Because a single airborne sensor turns a tight box on the surface into a lopsided board, where one side sees over the horizon and the other waits for updates that arrive too late to matter. Porter brought the MH-60R to life without spiking tensions. No warning shots, no aggressive turns, just a clean spin-up on the flight deck and a green light from the air boss. The Seahawk is a quiet statement that lands loudly in tactical terms. From takeoff, it extends the ship's eyes far beyond the radar horizon, gives the combat system an elevated node, and adds a flexible scout that can hunt submarines or prosecute surface tracks. It's non-escalatory by the rules, but every sailor on those four bridges knows what it means when a Romeo lifts. The helicopter's sensors stretch the map. Its surface search radar paints contacts that sea-skimming returns can hide from a ship-mounted array. The FLIR locks on exhaust plumes, hotspots around deck machinery, and the small visual tells that mark class and readiness. The ESM package listens for load patterns and pulse rates from fire control radars and navigation sets, then feeds bearing lines back to Porter. If needed, the crew can drop sonobuoys, but in a surface squeeze, they use altitude and speed to classify and verify. Now the destroyer isn't guessing what sits behind a hull. It's getting angles on masts, scopes on deck activity, and beams on emitters with far less clutter. Force multiplication is simple. The airborne node makes ship weapons smarter and faster. A helo-bearing line that intersects a SPY-1D range arc produces a high-confidence fix. That fix turns into a targeting quality track for surface weapons or for long-range missiles that demand precise updates. The helo can cue the ship can cue the helo, and together they preserve custody through maneuvers. One asset in the air compresses the loop from detection to classification to firing solution. 4 ships that rely on voice coordination cannot match that tempo without a higher node fusing for them. Payload ambiguity adds weight. The Romeo can carry lightweight torpedoes. It can also lace or mark for weapons, and it can provide mid-course updates that sharpen an anti-ship shot from the destroyer. The Russian captains now have to ask the hard questions. Do they risk closing when a helo can guide a weapon in? Or do they widen to force that helo to spend time flying, and less time holding a steady stare? That uncertainty taxes their plan more than any shouted warning. Timing mattered. Lift came at 5:32. Within minutes, the enclosure stopped contracting. The outer legs of the box eased their rates, and the inner pair bled a few degrees of heading to keep sea room. The risk math flipped. A tightening ring against a ship alone looked like leverage. A tightening ring against a ship with an eye in the sky looked like a trap, because any rush inward could hand the destroyer a clean, legal justification to lock out a threat lane and hold a firing gate with multiple cues. The deterrence logic is straightforward. The helo didn't say, "We're scared." It said, "We see." Eyes on masts means no surprise radar modes. Eyes on exhaust signatures means propulsion states are known. Eyes on fire control cues means any pre-launch dance gets logged and countered. The airborne perspective strips away the last hiding places of a surface formation, trying to look bigger than it is. And the cost? About $1,100 to launch and run a short sortie, give or take fuel and maintenance figures, against a group burn rate that ticks up whether or not they gain a tactical edge. Cheap signal, strong leverage. The Seahawk took a squeeze that risked a near-collision narrative and turned it into a distant shadowing routine where the other side spends more money and collects less useful data. The mini payoff came without a flare. The box relaxed. Encirclement became parallel trailing at safer distances. Porter kept custody of every track with better classification than before the launch. And air sat on our side of the ledger. If a single sortie could bend the arc of 4 hulls, the real prize comes next. The data those blades bought when the wakes finally smoothed out. 4 ships aimed to scare. Porter harvested a library. That was the trade the moment the box opened and the Seahawk went up. The standoff stopped being about hull counts and started becoming about entries in a database, pulse rates, scan patterns, beam widths, and the timing habits of watch teams on 4 different bridges. Intimidation puts pressure on people. Collection puts pressure on systems. Systems leave fingerprints.